Okay, so as I've already said, the links between programming and mathematics have always been very strong. I guess the people who pioneered computing actually were mathematicians who saw, to some extent, saw kind of early computing as a branch of mathematics, people like Charles Babbage and Alan Turing. And I guess when computing was first introduced into schools, it was very much like that. So in the early 1980s, when schools in England received their BBC Micro, generally it would be put into the hands of a mathematics teacher who would look at ways they might use it in the context of mathematics. And students who did computing in schools in that era, in the 1980s, were very sort of hands-on and under the bonnet of the computer with programming languages like BASIC and Logo. And I guess both in terms of the way that we use computers and in terms of computing in school, there's been a drift away from that. So with things like the Windows operating system, it was actually much harder to get to the point where you could, get some code into a machine and see what it did and play around with it. And likewise in schools, with the advent of the subject of IT, the emphasis in computing in school was about how to use programs and software. So learning how to use word processors, spreadsheets, and so on. Those skills are very important, and I guess very, very many jobs will require you to use some of those things at some point. But nonetheless, it's clear that there's less opportunities for being creative through using software compared to coding itself. So with obviously I'm talking in very broad and general terms here, but I guess hopefully we can agree that the amount of computing and hence programming taught in schools has reduced over time, and so the explicit link and this very intimate relationship between computing and mathematics has reduced as well. The number of students who get to appreciate that idea. And this issue has been raised in various reports. So there's an Ofsted report from 2008 which says it used to be the case that students would use computing as a tool to solve and explore problems. That's this idea of being underneath the bonnet in the code. And this is no longer the case. More and more, the student's been reduced to being a user of software, or even more passive than that, perhaps just sort of watching a teacher use the software and demonstrate mathematical ideas through that. I'm going to try this, but there was a film, an independent film was released just before Christmas called From Bedrooms to Billions, and it was all about the British computer games industry and how numerous young people, mainly men to be honest, in Britain were highly influenced by being exposed to computing in schools in the 1980s and computers at home, and just having the opportunity to explore and get into some very creative processes in code and mathematics through that. And part of the film has Ian Livingstone, who was responsible. He co-founded the Games Workshop, and he was very influential in the British computer games industry. He was responsible for the Tomb Raider franchise at IDOS, and more recently he's become a skills champion for the government, reporting to them on these issues in education. There's a very nice section from this film which I thought I'd try to share with you, and at this point Stephen's going to remind me that I need to stop recording, because although we've got permission to use this in a live event, we haven't got permission for it to appear in the recording, so I'll stop that. Okay, was anybody able to see that? Oh well, that didn't seem to work very well. In any case, what he was saying is that there's actually been a decline in applications to study computing at university, even though our world is becoming much more technology-based. And how have we missed this opportunity to get more and more young people interested in computing and mathematics? Okay, so and of course, more recently there have been various initiatives to get more and more young people interested in code. Any number of projects, the Teach the Hour of Code project, Code Club. This is a website where schools can get resources to set up their own coding clubs aimed at children from the age of 9 to 11. You can read any number of articles in the mainstream press about why kids should get access to code. And the Raspberry Pi is an example of this. students using Python and getting involved in electronics again through that, and people like Conrad Wolfram and Ian Livingstone speaking about how important these things are. So it seems that there's a great opportunity here to restore the link between code and maths. We have got more and more young people taking an interest in coding, but we want them to see that as part of mathematics and look at the relationship of the two things side by side. So there's a great opportunity here to reintroduce coding into the mathematics classroom, and this talk is about some of the work that MEI is doing in this area. So the major part of the talk will be about MEI's work to reintroduce coding and CAS, computer algebra systems, into the actual assessment of A-level further mathematics. As you'll see in a moment, this is a really significant breakthrough, because there's been much resistance to allowing students to have access to this kind of technology actually in the examination hall. But MEI, working with Texas Instruments and OCR, has managed to make that happen, and that's a key step perhaps in making this more prevalent in the whole of A-level mathematics perhaps, and beyond that. And then the second part of the talk is about ideas for exploring concepts in A-level mathematics through coding games, and this is some work that I've been doing as part of a maths club and in various enrichment sessions around the University of Warwick with Coventry schools recently. Okay, so I thought it was probably best that I would make sure that everybody knew what CAS was. So I'm going to be talking about coding and CAS, computer algebra system. So as a sort of 1 minute introduction to that, I guess what we can think of it as being a sort of algebraic version of technology to improve efficiency with numerical calculation. So technology has been used to speed up numerical processes for as long as we can remember. Calculators, the abacus, slide rule. So these are all technologies which enable us to speed up the process of numerical calculation. And I mean, there's much debate about the use of the calculator in the maths classroom, but I don't think many people would disagree with the notion that at some point, once you've got some mastery of basic arithmetic and processes, then these devices are hugely important to be able to speed up the process, to get results that we need, and to be able to get to the point where we can start to interpret results rather than being bogged down in that kind of process. So CAS is about extending that into algebra. So CAS can handle things like expanding and factorizing and simplifying expressions. It can do calculus, it can solve equations, it can work out limits of functions, and these are just a few things that CAS can handle. So the next thing I'd like to do is just demonstrate that too, just to give you an idea of what it actually looks like on the screen. So if I go here, I'm hoping that I'll be able to share Geogebra with you. So Geogebra is free software and it has a computer algebra system built into it. I think most people who use Geogebra don't use the computer algebra system part of it, but it is there nonetheless, and it's very powerful. There are computer algebra systems in lots of math software and calculators. Maple has it, of course. TI calculators have it. Any number of other calculators have a CAS built into them. And there are various other free CAS packages available on the web. Maxima is one that's quite popular. There's one called Sage. But however, we're looking at CAS here in Geogebra. I'd like you to just ignore the matrices on the screen and the slider on the right for the time being. I'll come back to that in a moment. I just want to give you an idea of what we can do here. So we can ask it to expand expressions, things like this. We can ask it to factorize expressions. We can ask it to differentiate things. And then we can ask it to solve equations as well. So We can ask it to solve it for complex numbers, which is something that we do get the students to do in the FPT module, and I'll come on to that as well soon. So we can ask it to find complex solutions of values. So you can see how this can speed up processes and enable us to focus on the interpretation of results. Another thing we can do with this is we can play around with parameters. So instead of looking at a particular quadratic, we can be varying the coefficients. We can be looking at completed square form. So of course, a deep understanding of something as simple as a quadratic doesn't mean just being able to look at a particular quadratic and be able to find its root and imagine its graph. It's also got to be about changing, across the family of quadratics as well. So changing the coefficients, looking at different forms of the same quadratic. And all of these things are much more naturally explored using technology. Okay, so I'll come back to that in a moment. Those are the kind of things that CAS can do. Something I wanted to give you an example of how CAS can enable you to access results that you wouldn't been able to imagine being able to get otherwise, and just enhance the quality of discussion in a maths classroom. And I thought I'd return to the theme of the other talk that I gave for the IMA, which was an online talk, which included a section on the Google PageRank algorithm. Now, I don't want to go through the whole of the detail of this again, but I'll refer you to the other talk for the full detail. But essentially, the way that Google assigns scores to websites, which in turn determine the position they will appear if found in a search, is a famous algorithm called the Google PageRank algorithm. And it's a really nice piece of linear algebra. So this diagram here shows some websites, website 1, website 2, website 3. There are various hyperlinks between them. And these hyperlinks, the way that they're set up, determine a system of equations, which are over here. I won't go into the detail of that. That's covered in the other talk. And X, Y, and Z here are the respective scores of the three websites. So they need to satisfy these equations. So X is the score for 1, Y is the score for 2, and Z is the score for 3. And we can see that that's the same as this matrix equation. So all of these ideas are accessible to a student, well, taking GCSE maths, I would argue, but certainly a student who's taking further maths and will have done some elementary work with matrices, and perhaps a student who's taking further maths in upper sixth who will have looked at things like eigenvalues and eigenvectors. Because of course what we can see here is that what we're looking for is an eigenvector of this matrix whose eigenvalue is 1. And there are lots of other sort of interesting side sort of snippets that students can look at here. Like this matrix, for example, is a stochastic matrix, so the columns add up to 1. And it means that its eigenvalues have got some special properties. There's a theorem which more or less says that all of its eigenvalues have modulus less than 1, but there will be an eigenvalue of +1. And you can see the eigenvector that we're looking for is the eigenvector that's got the eigenvalue of +1. And because all of the other eigenvalues are smaller than 1 in modulus, it means that we'll get convergence to that particular eigenvector, the one with eigenvalue 1, if we sort of iterate this process of applying the matrix to a seed vector. So all of these ideas are, interesting to students. They make what they're studying feel much more relevant. It gives them an application of eigenvalues and eigenvectors, which feels very real and relevant to their life, meaningful. And I'll just show you very briefly how we can look at that in CAS. So again, I'm just going to nip back into Geogebra now. And I think what I'll do is I'll just clear out everything we've got in the CAS window here. And start again. So you see over here on the left, we've got the matrix that you just saw on the screen. It's matrix 2 over there. What I can do is I can find its eigenvalues very quickly. So I can define a function f of c to be equal to the determinant of our matrix 2 over there minus c multiplied by the identity matrix of size 3 by 3. So that'll give us that. it's drawn a picture over here of the qubit, although we can't see the x or the y-axis. So now we can ask it to solve f of c equals 0. And you can see there we've got our eigenvalue of +1, and we've also got a repeated eigenvalue of -0.5 and no complex roots for that one. We can also do things like we can look at this idea of iteration. So I can do matrix 2 to the power of n times matrix 4. So if you see matrix 4 there is just some sort of seed vector with 3 1s in it. So if we do that, I'm getting a value here, but over on this side I can change the power of the matrix 2 that we're applying to that. So if n is 1, if n is 0, we're getting 1 1 1, and you can see that as we increase the power of the matrix that we're applying to it, we're actually getting convergence there. It's not very helpful to be given in fraction form, but believe me, that vector is converging to the scores of those 3 websites. So that's all very well and good, and we can do this very quickly. But there's still an issue in that so I'm trying to close down application sharing again now. There's still an issue in that this example is tiny. The world does not consist of 3 websites, and there's not enough there to really get a feel for what the algorithm is doing in terms of the end result. So maybe we might want to look at something a little bit more interesting like this. This is a much more valuable example because although it's only got a tiny number of websites, it's still far richer in terms of discussion and what we can learn about the algorithm from applying it. So again, if I jump back into CAS a second time and share this with you, what I want to show you this time, of course, is, so just trying to clear out this again, what we can do with the 7 by 7 matrix. So this matrix here is the one corresponding to the system of 7 websites, and once again we can define a function which is the characteristic polynomial of that. Matrix 1 this time minus identity 7 this time. Hopefully I've got my brackets right. What have I done there? Determinant. D. I'm missing a D. D times that. Oops. Let me just try that again. So okay, there we go. So there's our characteristic polynomial, and now I'll C-solve it because I reckon there's a good chance I might have some complex solutions to that. And you can see that I'm getting a whole load of values, well 7 of them I would guess, and you can see that the modulus of the values appears to be less than 1. There's 2 real ones and this complex one. I can see D equals 1 popping up there as a solution as well. So I can show students that the results that I'm referring to seem to be holding for a range of examples that are big and more convincing, and then we can go on and we can get some scores and so on. So this is one of the reasons that we're trying to promote the use of technology, is it gives us access to a range of results much more quickly and can put us into far more kind of extended situations than we would normally be able to be in the classroom. Another key point that we were trying to sort of capture when we were devising the Further Pure with Technology module is not only the point that I've just made, but also the very close relationship between rigorous mathematical thinking in the form of definition and proof and the skills that are of the same nature that are required to code. So I thought I'd put this example on the screen. And on the left here, you can see a very simple proof that if you take two integers which are either both even or both odd and add them together, the result is even. But you can see that the proof involves understanding exactly what it means to say that numbers are odd or even and checking against the definition. So in the FPT course, we'll get students to explore number theoretical ideas in which they'll need to capture these properties in the form of code. And so over here you can see equivalent Python code which just takes numbers from 0 to 10 and adds them and checks to see whether the result is even or odd compared to the input, and it just sort of prints something out about the result. But I think you would agree that anybody that can construct this, you know, needs a good knowledge of what it means to say that an integer is even or odd and so on, and checking for the result. You know, how does this integer part function work? And there's a very close relationship between this code and this proof over here. So again, in terms of deeper mathematical thinking, code seems to be a very good way to access those ideas. Okay, so now I want to talk about FPT itself and what it actually looks like. And the background to the FPT module, Further Pure with Technology, is that technology is just not used as much as we'd like it to be in the classroom. So in A-level, students can have access to a graphical calculator in all but one of their exams, but the exams themselves are actually designed so as not to give you an advantage if you have got a graphical calculator. And of course the obvious consequence of that is that if it's not giving you an advantage in assessment, then many teachers, understandably, teachers are people who are under a lot of pressure to deliver a lot of content to a lot of students working at a lot of ability levels, you know, they won't exploit it as much as they might in their teaching. It seems that only when you have the use of technology as part of assessment will you start to see any significant changes in the way that technology is used, in a sort of widespread sense in the maths classroom. So there are no exams where programming environments or CAS were allowed up until recently. And so MEI wanted to drive that debate forward and explore whether you could actually allow access to programming and CAS in an exam. You know, whether we could satisfy awarding bodies that this is fair and it's not open to, you know, cheating, I guess. There were concerns that if students have access to computers in exams that they'll kind of be able to get online and access help through that, all those kind of issues you can imagine. MEI wanted to take that debate forward. And so as a result of that, the module Further Pure with Technology was established, and it's an A2 Further Pure Mathematics module. So it will generally be studied during year 13 by only by students who are taking further maths. But remember, there are a good sort of 15,000 students who are now taking full A-level further maths in England. It's up hugely from around about 2000, when there were perhaps about 4,000 or 5,000 such students. It was developed with the support of OCR, the awarding body, and Texas Instruments, and MEI is very grateful for that. And it will inform approaches to use of technology in future developments of A-level. So, of course, A-levels themselves are changing, and so MEI is very keen that the work it's done with Further Pure with Technology is not lost as a result of that, and it won't be. And I'll come on to that again soon. The first exam of FPT was back in summer 2013, so there have been 2 papers so far, and I want to show you a little bit about what it actually looks like as well. In FPT, students are allowed access to a programming language. That could be a programming environment within a calculator, like the TI Inspire, for example, or it could be Python, or it could be the programming language within Maple, perhaps, as well as various other options. A computer algebra system, already mentioned some of those, a graph plotter, and a spreadsheet program. And the criteria for content to be included in this module is that the topics that are there should allow the use of technology to allow access to a large number of results very quickly, and particularly exploring, you know, whole families of functions, for example, by changing parameters, that kind of idea. and put the emphasis on making inferences and deductions based on the results that the technology is giving you. So rather than spending time on the process of generating the results, assume that the technology can get you those very quickly, and ask the students to think about what they're seeing and test them on that. And also the topics that are included in FPT had to not be included elsewhere in A-level maths or further maths. So that was quite a restriction actually, but it also opened up opportunities to do things that haven't been seen before in A-levels, things like number theory. So number theory is one of the sections of content in FPT, alongside investigation of curves. So the idea that we can get students to look at much more sophisticated curves, parametric curves and polar curves and so on, that without technology it just wouldn't be sensible to study. Functions of complex variables, so the very idea that we can define functions on complex variables and we can still differentiate them, and sign is defined on the complex domain. Those kind of ideas students access in FPT, and then number theory. And I've already said something about parallels between number theory and proof and code. Here are some examples of the type of things that students might do. So they're looking at a polar curve, they're using the technology to get an expression for the gradient much more quickly, and they're sort of trying to describe what happens to the tangent as you move around the circle. We're looking at this function of a complex variable and restricting that to a particular domain and seeing what happens there. Writing programs to test whether where we get pairs of integers separated by 2 are both prime. These are the kind of things that we might ask students to do in an FPT exam. I thought I would show you a past paper and try to just answer parts of it. So again, first of all, we'll start with Geogebra and graphing software and CAS, and then we'll have a look at an example using Python. So I'm hoping this will work reasonably well, enough for you to see what's actually going on. So what we've got here is, again, apologies if this doesn't work particularly smoothly, but on the right here there is an image which is an exam question. I think it was from I think it was the 2014 paper actually, the one from last summer. And this question has been designed to be done using plotting software and CAS. So you can see that we've got to look at a family of curves. We've got a cubic on the top. This is x cubed plus ax squared plus 1 divided by x to the n. And if you read through the question, we've got to look at it in lots of cases when a is 2, 3, 4, and the power of x on the denominator there at some point is 1, and later on it becomes 2 and 3. So the kind of thing we might expect the candidates to do for this are as follows. So I'm going to go to the graphics view. The first thing I want to do is insert some sliders, and this means I'll be able to vary the values of the various parameters that vary throughout the question very easily. So I'm going to have one called A, which is only going to take the values 2, 3, or 4, so min 2, max 4, and an increment of 1. So you can see here I can just play around with this now and change that value. Again, I'm hoping the technology is performing well and it's keeping up here. And then similarly for the power of x on the denominator there, which is going to be either 1, 2, or 3. So I can set up a slider for that. And now I can define this function. So f of x is going to be equal to x cubed plus a times x squared plus 1 divided by x to the power of n. And of course, when I plot this, I'll get the particular case of a being 3 and n being 1. So you can see we've got a graph there. And to begin with, I'm varying a. So if I look at this, when a is 2, when a is 3, when a is 4, perhaps if I zoom out, that might be helpful. Okay, let's do that again. So when a is 2, when a is 3, and when a is 4. we've got to describe some common features of the curve. So I guess we can see that we've got a minimum here with a positive x coordinate in all cases. We've got a negative real root, it seems, of f of x equals 0 in all three cases. So there's various things you might say about that. And it says when n equals 1 and a equals 3, find the number of stationary points. Okay, well this is great. We can jump into CAS over here and we can ask it for, well, let's define g of x to be the derivative of f of x. So you'll see there that that is completely dynamic as a function of where my sliders are. So if I change my sliders now, that derivative changes as a consequence of that. But I'm interested in n equals 1, a equals 3 at the moment. So I could ask it to solve g of x for stationary points. I guess I probably want to get the second derivative as well. So let's call that h of x. Probably want to look at what happens if h of minus 1. So that's equal to 0. So the second derivative test is not conclusive for that point. Could still be a max, min, or a point of inflection. So I might look at g of minus 0.99. So what's the gradient either side of x equals minus 1? G of minus 1.01. Oh, it's negative on both sides, so it's a point of inflection. So these are the kind of things that we might expect students to do with CAS and curve plotting software. I think I've basically got about halfway through that question by doing those things. And in terms of coding, let's have a look at an example of that. So this is where I need to jump into my browser. Okay. What I'm sharing with you now is a really nice online sort of integrated development environment for Python. So quite often when I'm working with younger students, this is the way that I'll start using Python with them. So it's split screen, so you can type your code on the left, you can run it, and you can see the output on the right. There's no installation either. This is just a web page available through the Code Academy website. So it's great for just getting up and running immediately. So what I've done here is, as a comment in my code, I've reproduced an exam question. So it's about arithmetic modulo 17. It says x and y are numbers from 0 to 16 inclusive. We're looking at solutions of, that should be equals there, I think. So we've got to make a program which will explore this equation, modulo 17, a, b, and c are positive integers. But actually I can see that I'm going to be asked to have a being 1, b being 5, and c being 13 as well. So this is what we might expect. And Python's really nice language to introduce students to coding with. Many of those projects are based on Python that I talked about earlier. But Python forces you to be really neat. So it uses indentation as a way of indicating the logical flow of the code and the dependencies, if you like. So this is what we might expect to see as a solution to this. So we're going to define a function with 3 parameters. It's called test, and it's got 3 parameters, a, b, and c, 3 arguments. And what it's going to do is it's just going to run through all these values of x and y between 0 and 16 and just test that equation for all of them. And it's going to output anything where it works. So I is going to go across that range. That'll take it from 0 to 16. It won't include 17. Similarly for j, and notice the indentation there, so that this loop is sort of inside it's nested in the other one. And indentation again, so we're just going to test the condition if a times I, a times I plus b times j modulo percentage 17 is equal to c. I need a bracket there to complete that calculation. Then, and again that's indented because we'll only do this if that if statement is true, print ij. Hopefully I can now run this and test this with a being 1, b being 5, and c being 13. hit run here, and out on the other side there I get all the values of X and Y, which are solutions of that. So that's the kind of thing that we might get students doing. And you might think, well, that's kind of fair enough, you know, it's a decent skill to have, and it tests some understanding of the mathematical ideas underlying that. But what about, so I don't think I've included a slide about this, but if you look at some of the past papers, and you can access these through the MEI website, you'll see that in these questions, students are continually moving between using the technology and then interpreting their results. So there are other parts of that question where they have to actually do some pen and paper proof. So they've explored what solutions might look like using technology for a limited range, and then they have to do something which actually the technology won't help them with, and they're using the things side by side. There's more information on the MEI website. You can get the specification, past papers. There's information about this on the TI Inspire website. Project Euler is a great place to start students with coding and using spreadsheets to solve interesting mathematical problems. So far, as you might expect for something as kind of radical as this, I guess, the uptake is not enormous. There are about 10 schools with students doing this year. MEI's got produced teaching and learning resources for it. They're available in Integral, and many thanks to the University of Bath as well for their support this year, because they're providing an equivalent set of resources for using Maple for FPT, which is very exciting, and we're going to try to trial those in some schools next year too. The future, so certainly further maths will have elements which are like FPT in it, and that's something that MEI obviously will look very carefully at, learning from the experience of FPT. And there's also this statement about the use of technology in AS and A-level mathematics, so you know, outside of further maths, but in A-level maths itself. The use of technology, in particular mathematical, statistical graphing tools and spreadsheets, must permeate the study of AS and A-level mathematics. And there's a lot of thought going into how that's going to be brought into effect too at the moment. But there are some positive things there about the future of this work. Okay, I think I've just got a few more minutes left now, so I'd like to finish by just telling you about some other work that I've been doing, which is trying to introduce students to, you know, perhaps difficult for them mathematical ideas in the context of code, and in particular in the context of programming a game. There are plenty of young people who are interested in doing this, so it seems like if we can connect what they're doing to mathematics for them, that's a good thing to do. The software that I've been using for this is called Game Maker. It's free. It's really easy to install and get started, and the reason I like it, the main reason that I've been using it, is because there's a very quick turnaround between just having an idea and then actually getting something moving on the screen, so seeing the effect of your code. But it is actually used by professionals as well. There's been 3 or 4 massive indie hit games which were produced using Game Maker, so that's a good thing too. It's a proper bit of professional software as well, with a good free version available. Okay, so what I wanted to do first of all is show you how quickly you can go from a blank project. So this screen that you're looking at now is a blank project in Game Maker to having something up and running on the screen. So I'll try and do this as quickly as I can, but I'm trying to demonstrate that this is actually quite a simple process. Okay, what I'm doing first of all is just creating a sprite for the main character in our game. So it's just going to be a black circle. I'm going to make it center like that. So that's what the character is going to look like. I'm going to create an object which is going to look like that sprite, and I'm going to give it a bit of functionality. So I'm going to say every time the user presses the right key, we will have its x coordinate increased by 5. So if the player just holds down the right key, it will just keep increasing, with that being applied every frame in the game. I think there's default 30 frames a second here. Okay, so, and then the only other thing I need is a room. So I can put my object in the room, and that should now be ready to play. So I can get it to compile that and make it happen. This is a HTML5 version of the game we're looking at, so I'm going to need to hop over there now. So coming out of application sharing and back in, so I can show you my browser. But hopefully, here's our game. It's just arrived in the browser. I'm hoping you can see this, and you can see there's just a black dot there, and you have to believe me, but I'm now pressing right, and you can see that it's moving right. So it's really quick turnaround between just opening up the software and getting things moving on the screen. That's what's so good about this piece of software, I would say. Now, what kind of mathematics can you get students to explore, even with ideas as simple as that? So let me show you the kind of things that I've been doing with some students as examples of this. And these are the kind of ideas in mathematics that we've been exploring. So some very basic ideas about vectors, some ideas about position and velocity and acceleration and relationship between those things. We've been looking at behavior of sort of unusual functions with limits and asymptote type behavior, the notion of an inequality, the graph of sine, and the equation of a circle. So we've been exploring all these things, but coming in from the root of motivated through using the software to get some game type activity on the screen. Let me show you the examples then. Okay, so I'll put this together so that I can sort of flick between the examples. Now, you can see there that I've put a graphic in which is the code underlying the behavior of this black dot. So when I press the right key, 5 is going to be added to its x coordinate and 2.5 is going to be added to its y coordinate, whereas if I press left, the opposite will happen. And so now I'm going to press right, and you can see the behavior of the dot there. The y-axis is going down because it does in computer games, in case you're wondering about that. And if I press left, black dot moves this way. So obviously this is completely trivial in terms of its level of mathematics, but nonetheless, students can start to explore vectors like this. We could ask questions like, well, what if the 2.5 becomes 10? What if the 2.5 becomes -5? We can ask them about, what angle do you expect it to move at? Is it going to be a big angle? Is it going to be a 45-degree angle? Those kind of ideas. And we can get them to play around with that. We can look at the behavior of the dot, and we can learn a lot of things through that. I'm not sure whether I'll do this one's quite a nice example. So for this object, we've got an initial a variable called a, which is set to 0 upon the creation of the object. And then every time we press right, we'll add a onto the x-coordinate of this, and we'll also add 0.1 onto a. So of course, if we press right now, I'm not sure how well this will show up on your screen, we should see this dot accelerating because the amount we're adding will increase. If I press left, it will just move left at a constant velocity. So again, we can ask students, why is this happening? We can maybe get them to look at this and predict what's going to happen, and we can get them to think about what we mean by acceleration and velocity and so on. Trying to think which examples I'm going to do. Oh yeah, this is quite nice. So here, when we press right, we're going to add on this to our x-coordinate. So you can see the closer our x-coordinate gets to 500, the less it wants to move towards 500. And so if we press right, we can see this thing sort of really resisting going up to 500 and then move back constant velocity -5. As a final example, perhaps this one, I haven't really formatted the code very nicely here, but in this bit of code we've got a circle drawn at center 400, 200, radius of 50 in an outline form, and then we're going to just we set this up so that we can move the dot with up, down, left, right, so doing the appropriate addition, subtraction from its x and y coordinates for that. But here we're going to say, if this is true, we're going to say in the circle. If this is true, we're going to say not in the circle. So you can see we're not in the circle. We can move the dot in. We're now in the circle. We're not in the circle. We're in the circle. And again, we can ask students what's going on here. Why is it we're using this square root thing? Hopefully we'll see some kind of connection with Pythagoras' theorem. And I would argue that this is a much more powerful way of introducing something like the equation of a circle than saying, here's the equation of a circle, it's the thing that's satisfied by the x and y coordinates of this thing. Try to imagine everybody x and y changing, but to come in from this kind of approach is, again, much more meaningful to students perhaps, and especially those who are interested in code, because they might say, well, I can see that I can actually use that in my coding project that I'm doing at home, you know, and it's important. I can see that. So I'm hoping that all stood up reasonably well, but I think that's all I want to say actually. Hopefully I've convinced you that there are, you know, a lot of opportunities for the promotion of maths through these kind of methods, and that MEIs hopefully get a key player in that and doing some interesting work. But I think I'll finish there. And are there any questions or comments? Oh, that's a good question. Right, so here's me raving on about students being able to have access to technology in the exams. However, when they leave the exam hall, they hand in a piece of paper that they've written on by hand. So they will have to reproduce those graphs using pencil and pen. They will actually have to write out their code using pencil, pen on paper and hand that in. So that's another obstacle to overcome, but not there with that just yet. Of course, there's a lot of leniency in terms of the way that would then be actually marked, I guess, in terms of the exact syntax in programs, for example. Okay, well, I hope you found that interesting, and if there are no further questions, I guess I'll thank you for attending and say goodbye.